Okay, in this presentation we're going to continue on with an exercise based on what we have here. So this is the second part of this exercise. So we've simulated a data set, and what we've done is fitted three models to that data: an AR1 model, an AR3 model, and an ARMA11 model. And we've selected the best fit of those three models, which is AR3. And essentially we're going to pick up from there. So essentially what we're going to do now is carry out a residual analysis and look at this Ljung-Box Portmanteau test. Okay, so we've done all of these exercises A to F. We're going to pick up on F again, and we're going to carry out these analyses here. So G, determine the corresponding 95% confidence interval for the AR1 model fitted above. That's an F, so that's why we're picking up an F. Mention the best fit model from your observation in exercise F. Calculate the predicted values using the best fitted model above for the next 10 steps ahead. Construct the autocorrelation function and the sample autocorrelation, partial autocorrelation function for the residuals of the best fitted model. Comment on the graphical outputs, and then what we're going to do is perform the Ljung-Box Portmanteau test for the residuals of the model with lags 4, 6, and 12, and comment whether this model is appropriate. We're going to use lags equals 4, 6, and 12, and also fit DF equals 3. I'm not going to go into the details too much about what fit DF is. We're just going to use an overall, have a broad view of this test. But it is actually interesting to sort of break it down into detail. We won't have it in too much detail here because of time, but you know, it's well worth looking at fit DF3. Why do we do that? Not going to be explained here, but worth checking out. So let's go back down to where we've finished. We are here. So we are fitting three models to our observed data set. This is the AR1 data. A data set that we create is called observations. We're using ARMA as the function to fit these models, and we're fitting three models. This is our AR1 data set, and our AR1 model, I should say, and fit 1. AR3 model, fit 2. And ARMA11 model, which is fit 3. We finish off by looking at these AIC values to sort of determine which of these models was the best fitting, and it turns out it's fit 2. Its AIC metric is much lower than the other two. So maybe that's good, maybe it's not. We'll find out. So that's where we're going to sort of pick up from. So we're going to look at the determining the corresponding 95% confidence interval for the AR1 model. Now that's actually fit 1. So we're just going to go with fit 1, even though it's not the best fitting model. It's what we're asked for. So just going to sort of set this up very quickly. Quantiles, which is minus 1.96 and 1.96. So essentially we're just going to set that up as a little vector there called CZ, quantile Zs basically. And that is a little vector containing minus 1 and 1 times Q norm of 0.975. And that gives us minus 1.959 and 1.959. Okay. So that's what we're asked to do basically. It's just to sort of quickly set that up. So we have our quantiles. The variance covariance matrix of the estimated coefficients from the fitted model. So we have fit1 $var.coef. So these are the variance coefficients, and we're just going to extract them from fit1. That's the fitted model, and we have these terms there. Particularly what we're interested in is the first row, first column, which is the top left, essentially 1.8841. That's the variance estimate. We're going to use the standard deviation when we calculate the confidence interval, so we're going to use the square root of that expression there. So that's it. This is what we have. Determine the corresponding 95% confidence interval for the AR1 model. So it's fit1 $coef 1. That's the first element there. That is the slope estimate. Z's is the quantiles, minus 1.96 and 1.96, and square root of fit1 $covar, that's essentially the square root of the variance. That is the standard deviation that we are looking for. So when we add them all together, we get this two values here, the upper bound and the lower bound. 0.9988 and 1.005829. Okay, so that's our confidence interval right there. Okay, so we can move on. So just as a quick remark, we are asked for the best fitting model, which we discussed previously. That is fit 2, the AR3 model, and that's because the AIC value is the lowest. What we're going to do is fit the next 10 values for that model. So predict fit 2, that's our model. N ahead is just the number of steps ahead, and when we fit that and get the predictions, we get these numbers here. Now we'll move on from that because I think we've got everything done there and we've got plenty to do beyond. So we're going to plot the ACF and the PACF for the residuals and interpret them. So that's the next exercise after this. But let's just plot them first. So we extract the residuals from the best fitting plot. That's fit 2. So we have fit 2 $ residuals that extracts all the residuals. We're going to plot ACF and the PACF of the residuals. So that's what we have there. And we're going to position them side by side. So we have par MF row equals C. 1, 2, which is a single row with 2 columns. That's a setup to allow this grid setup here, this side-by-side orientation that we can look at them side by side. Okay, so we'll move on from that and we'll interpret them. The PACF for the data shows no significance from lag 2, which could indicate stationarity, but the ACF is decaying very slowly, indicating that it's not stationary. For example, this is consistent with ARMA 111 behavior, or ARMA 111 behavior if you want. This plot for the residuals generally lies within the confidence intervals. This is consistent with the residuals forming the white noise process. Okay. So we'll move on to the last part here. This is the Ljung-Box Portmanteau test. So a quick description of it is worthwhile. I won't get into all the details here. Just remember we're told to use particular specifications in the question. Lag equals 4, 6 and 12 and fit DF is equal to 3. And won't explain too much why in this particular instance, just to get a general idea of this test. The Ljung-Box Portmanteau test is used to determine whether the residuals from a time series model are independently distributed. In simpler terms, it checks if there is any autocorrelation, which is correlation over time, in the residuals in your model. So here's what the test does. The null hypothesis is H0, the residuals are independently distributed, no autocorrelation. Alternative hypothesis H1, the residuals are not independently distributed, that is to say autocorrelation is present. So if the p-value from the test is low, typically less than 0.05, it suggests that there is significant autocorrelation in the residuals, meaning your model may not be capturing all the patterns in the data. It's a useful diagnostic tool to assess the adequacy of a fitted time series model. If autocorrelation is detected, you may need to reconsider your model or include additional terms to capture the underlying structure of the data. Okay, so that's it. In broad terms, what we are looking at. There's a couple of details that we'll have to sort of skip over just for the sake of brevity. So we're told to use lag equals 4, lag equals 6 and lag equals 12. So fit 3 test models. We're going to be told to use fit df is equal to 3. There's a reason for that. It's just to sort of fine-tune the model according to the number of parameters. So we're just given a hint to use that. Why and the rationale behind that would require a full video. So it's a box.test. We're going to use the residuals from model or fit 2. So fit 2 $ residuals. And it's a Ljung-Box Portmanteau test. So its type equals lung. I hope I pronounced that correctly. So the results. If the p-values are less than 0.05, it suggests that the residuals are not white noise and further model refinement may be needed. So we decided fit 2 was the best fitting model of those 3 models, okay? But we're going to sort of test it out and sort of see, is it the final product? And this is what this test does, okay? So let's look at box test 1. Ljung-Box test 1, fitted 2 fit 2, residuals, type equals Ljung, fit df equals 3, lag equals 4. And the p-value there is 0.01565. Okay, let's just go back there a second. If the p-values are less than 0.05, it suggests the residuals are not white noise and further model refinement may be needed. So we have come across this eventuality, so we do need to carry out some further model refinement. Let's see what the other two tests give us. So this is lag equals 6, and we get a p-value of 0.03892. Same result. Okay. And 12, the p-value is 0.04057. So in all three cases, we get a p-value less than 0.05. So we get three significant results here. Okay. So let's reconcile all of the results that we have gathered up. So first, let's look at the previous ones before we looked at the test. The result above suggests that the residuals are forming a white noise process, suggesting a good fit for an AR3 model or an ARMA 300 model. The results above also suggest that the model requires differencing as it is consistent with an ARMA P1Q behavior. However, these tests, which are the box tests that we've just carried out, these tests are not consistent with the ARMA 300 model at the 5% significance level, since the p-values are less than 0.05. Thus, there is not enough evidence to conclude that the ARMA 300 is a good fit. Okay. Also, we would expect the ARMA 111 model to be used, that was used to generate the data to satisfy this test as well, and this can also be shown to be a good fit. Okay, we're not going to do that because we have done a lot of work today, but essentially just sort of unpacks all of the possibilities that we can work with. Okay, we'll leave it there.